Hello, Intro to Calc. Hope you guys are having a fantastic day. I'm going to be a little quiet today, and also awkward things might happen because I'm like in a conference room right now, so I might get kicked out, so I might have to move. But anyways, um, couldn't find a quiet space to work. So anyways, we are moving on to Chapter 2, Section 3, Day 2 of Calculus a Single Variable, and we are going to be doing the second day of the derivative function. And so the first day, 231, was about how to graph the derivative function, and today we're going to talk about algebraically how to get the derivative function. So that's going to be our goal, and then after I show you the long way to do it, I'm going to give you a couple shortcuts for a few different types of functions. You will have to be able to do it using the long method as well, so just make sure that, you got both. So number one, we're going to do, so this is the long definition of a derivative. It's using the limit, right? So remember that the limit definition of any derivative is basically, right, the difference quotient, taking the limit as h goes to 0. Remember, and the idea here is this is like the y2 minus y1 divided by x2 minus x1. And it's just the average slope over a distance of h on the x-axis, but we're making that value of h smaller and smaller and smaller and smaller, making it really, really close to 0, which is where we get the derivative function. So up until this point, we've only done the derivative at a point using the limit definition. And so that was like if x, if my x value is 2, then I would do the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. And in this case, we are just doing the case where x is equal to x. So we're doing it at any value of x. So basically, once you get the derivative function for a particular function, you can use that derivative function to find the derivative at any point. So I'll go through it and show you what that means. So basically, you're just doing everything but with x's instead of numbers, and you should be able to get a function at the end of it. Let's try a couple examples of that. So we're going to use the limit definition of a derivative to find f prime of x if f of x equals 3x minus 1, and then also do it for x squared minus 2. Now, if you think you already understand it, you can pause right now and try it on your own. Otherwise, I'm going to go through this for the next couple minutes. Okay, to use the limit definition, you need that difference quotient that I give you in the notes and that we've been working with all year. So you take the limit as h goes to 0 of f of x plus h minus f of x over h. In this case, f of x is 3x minus 1, so that means f of x plus h. I'm taking my x plus h and replacing x with x plus h. So it would be 3 times the quantity x plus h minus f of x, which is just 3x minus 1, divided by h. Okay, so I wanted to be careful not to use an equal sign here. I'm just using an arrow because this thing here does not equal the limit as h goes to 0 of this thing, mainly because I'm being lazy and I'm not including the limit. I will include the limit when I get down to my final answer, so don't forget to take the limit as h goes to 0 when you get down to your final answer, but I'm just going to use arrows at this point because I'm lazy. So basically at this point we want to distribute the 3 and then be careful of your negatives, so this should be minus the entire function f of x. So I kind of grouped the function f of x here because you should distribute the negative to both terms. So then you just simplify, and at some point you should be able to cancel an h out so you're not dividing by 0 anymore, and then cool, and that'll be easy. Okay, so in this case, right, once you distribute the 3, your 3x and your minus 3x and your minus 1 and your plus 1, those all cancel. So you end up with 3h over h, and then your h's cancel, so that equals 3. And don't forget that you're taking the limit as h goes to 0 of your final canceled version of the difference quotient. So the limit is h goes to 0 of just 3. There is no h in there at all, so there's no 0 to plug in anywhere, so your answer is just 3. So that is actually the derivative function of f of x equals 3x minus 1. And basically what that means is no matter what x value I'm at on this function, the rate of change is going to be 3. Now that makes sense because this equation here is a line and it has a slope of 3, right? And when you have a line, right, it has a constant slope. And so the slope isn't changing, so it should be 3 everywhere. So that works out the way that it should. B, on the other hand, is a quadratic function, right? So it's a parabola, and that, right, the slope of that is going to change depending on where you are on the graph, because like at the vertex, the slope is 0, and on half of the graph you have positive increasing slope, and on the other half you have a decreasing slope. So you are going to have an actual a function that is not just a constant number. So go ahead and try this one if you kind of understood how A worked. Go ahead and try to figure out B. Okay, so here's your answer. So if you tried it on your own, check your work, and if you got it right, you probably don't need to worry about listening for the next minute or two. You can kind of skip forward. If you did not get this correctly or you didn't try it on your own, kind of go through this with me. So we want to take the limit as h goes to 0 of the difference quotient here. And in this case, f of x is x squared minus 2. So f of x plus h is x plus h squared minus 2. So that's that first term. And then f of x is just x squared minus 2. So I'm subtracting these two. Again, be careful of your negatives. Distribute the negative into x squared, and then that should be a plus 2. So what ends up happening is my x squared and my negative x squared and my negative 2 and my positive 2, those cancel out. So I'm left with 2xh plus h squared divided by h. If you didn't get this part, you probably forgot to FOIL x plus h squared. So then I can pull out an h from the numerator, divide it, the h, h times 2x plus h over h. The h's cancel, and I'm left with 2x plus h. Again, don't forget about your limit, so you want to take the limit as h goes to 0 of 2x plus h, and that equals just 2x, right? You just plug in 0 for h. And so this is the derivative function of this graph. And basically what that means is if I want to know what the derivative is at any given point, like say for example, I want to know what's the derivative at x equals 0. You can take 0, plug it in for x, and you get 2 times 0, which is just 0, which like I said, that's at the bottom of the parabola where you have a slope of 0. And like if I want to know what is the slope of the tangent line at x equals 4, I just plug in 4, and I have 2 times 4, it's 8. So the slope of the tangent line, or the derivative, same thing, at x equals 4 is just 8. So anyways, it's a nice way to answer those questions about the derivative at a single point, because now you just have a function and you can use it for any given point. So that's cool. Okay, so once you get the hang of the limit definition of a derivative, then I will allow you to use some of these shortcuts. So the derivative of a constant function. So if you have any questions about the validity of these things, let me know in class, and I can prove to you this is true. But the derivative of a constant function, so a constant function, for example, might be y equals 4, right? Because 4 is a constant, y equals 4. So that graph looks like a horizontal line at 4, right? And so the derivative of this graph is always going to be 0 because it's always a horizontal line. The slope is always 0. So the derivative of a constant function, or the derivative of a constant in general, is always 0. So let b be a constant, just a number. If f of x equals b, then f prime of x equals 0. Next is the derivative of a linear function. So if you have the highest degree of x is just 1, so you have like y equals 5x plus 7 or something like that, right? Like we saw in example 1, the derivative should be the slope of the function. So f of x equals 3x plus 1, the derivative is just 3. So that's the case for any linear function. So again, if f of x equals mx plus b, and m is the slope and b is y-intercept, then f prime of x is just m, or just the slope. So hopefully both of those make sense. This next one's kind of a shortcut that I probably, just because this is intro to calc, I probably won't prove to you, but it's something that's really, really useful. So a power function is anything that's like x to a power. You can have like, I don't know, for example, y equals 5 times x to the 7th or something. That's a power function because you have a power on x. There's a constant out front, which would just be like a vertical stretch or compression. But generally speaking, this is the general form of a power function. And so the cool thing about the derivatives of power functions is you can actually just take your exponent, drop it down by 1. So that would be, it used to be x to the 7th, so now it's x to the 6th. And that number, the 7, gets multiplied by the number out front. So 7 times 5 is 35, x to the 6th. So y prime, in this case, would be 35x to the 6th. So that's kind of a nifty thing and really useful for a power function. All right, so here's your general form. So let b and n be constants. If f of x is b times x to the n, then f prime of x is n times b, so you take the exponent down and multiply it to the constant out front, and then you drop the exponent by 1, so that's n minus 1. So a quick useful power refresher is that negative exponents change where the base is. Okay, let me just show you instead of explaining it. Okay, so just a refresher, like x to the negative 3 is the same thing as 1 over x to the positive 3rd. And similarly, right, 1 over x to the negative 2 is the same thing as x to the positive 2 in the numerator over 1. So that's kind of something that will be useful. Also, the square root of a number is the same thing as raising it to the 1/2 power. So square root of x is x to the 1/2, cube root of x is x to the 1/3, and the fourth root of x is x to the 1/4, etc. So that's kind of useful for using the power function rules. So go ahead and try the following examples on your own, and then using the shortcuts instead of the limit definition of the derivative, and then check your answers. All right, so here are your answers. So in this case, right, you take each individual term and take the derivative. So x cubed, you take the 3 out front, and you drop the exponent by 1, so it becomes 3x squared. This x squared becomes 2x, and then this x just becomes 1 because it's x to the 1st here that you don't see. You take the 1 out front, and so it's 1 times x to the 0th, and x to the 0th is just 1, so it's 1 times 1 is just 1. And then the derivative of a constant or a number is just 0. Similarly, f prime is going to be 3x squared minus 4x, so drop the 2 down, plus 3. And then the last one, which is why I went over those derivative rule or those exponent rules, is that you have 1 over x cubed is the same thing as x to the negative 3rd. So I would take the negative 3 down as a constant out front, so negative 3 times x, and then I have to drop my exponent by 1. So it becomes, and if I want to get rid of my negative exponent, that just becomes negative 3 over x to the positive 4th. And that's pretty much it. Yay, shortcuts. That's cool. Okay, bye.